Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 7.2 from your textbook, which investigates how to integrate different types of trigonometric integrals. In the previous video, we worked our way through section 7.1, which basically showed us a new technique, integration by parts, that allowed us to manipulate or change the integrand of an indefinite integral so as to make it basically a simpler integral to actually be able to perform. In this section 7.2, I won't necessarily call this a single technique. We're not going to be learning just one technique here, but instead we're going to be learning some different approaches for different types of integrals that involve trigonometric functions. And these are pretty interesting in their own right, so we'll basically sort of handle cases where we have products of sines and cosines, and then we'll talk about products of secants and tangents, and then we'll talk about just some other sort of miscellaneous cases. This is in some ways, this is investigating just extending our knowledge of integration a little bit further, but also this section is really, really important for what comes next. In section 7.3, we're going to investigate another more general integration technique called trigonometric substitution, which basically always results in a trigonometric integral. So having this section 7.2, where we'll sort of study how to integrate things that involve powers and products of trigonometric functions, is going to be really necessary for the next very sort of general technique we'll be talking about. So let's jump in and take a look at some examples here. So to start with, we're going to start with a sort of motivating example to get the sort of general idea of this beginning part of this section. So we're going to try to perform the indefinite integral, the integral of sine to the fourth of x times cosine x dx. Now this is a pretty messy expression. I mean, this is the fourth power of sine times cosine of x. It's a product, which we know integration doesn't generally do very well with. We might be tempted to try something like integration by parts on there, since that's what we've just learned. But we should recognize that there's actually a very nice and easy way to do this. And it's namely the very first technique you ever learned, which is u-substitution. If you notice, the derivative of sine of x is cosine x dx, which means that we can just directly substitute into this and change this from this messy expression that has a product of powers of trigonometric functions into just a simple polynomial expression. So let's see how we would do that. Let's go ahead and let u equal sine of x, and we're sort of sure that that's a good choice because we know that the derivative of sine of x is cosine x dx, and that's exactly what we have back here. So just actually maybe make that a little visually easier. Let's go ahead and underline like that. That's exactly what we have there. So if we substitute then, this entire part, which made part of the product, is going to just be eaten up as this du. So when we do this substitution, we're going to end up with the integral. Instead of sine to the fourth, we're now just going to have u to the fourth. And then this entire expression here can just be thought about as du. So notice that this substitution not only removed the trigonometric functions, but it also made this so that it's not a product anymore, right? In other words, this cosine of x was completely used up to do this substitution. Now it should be very easy to do this using power rule, 1/5 u to the fifth plus c. And then we can just pop that sine of x back in there. So we get 1/5 sine to the fifth of x plus c. And there we go. We went ahead and performed that integration. Okay, so this tells us sort of a general strategy when we see products of sines and cosines. If we can get a single sine or cosine, then we know that that's the derivative of the other trigonometric function. Sine is the derivative of cosine, except it's got a negative value, and cosine is the derivative of sine. So if we can isolate a single instance of one of the sine or cosine functions, then we can perform this u-substitution. So let's look at some more interesting examples that require a little bit of modification before we can do this trick. So here's another product of sines and cosines, except it's even a little bit more complicated. Now we have sine cubed times cosine to the 6th x dx. Once again, we'd like to do our u substitution, but we shouldn't do it from here. If we try to substitute, say, like u equals sine of x, well, that'd be nice for this, but then we'd have to deal with this cosine to the 6th in terms of u, which might be very messy. And same thing if we try to do u equals cosine x, then that would handle this component, but then we'd have to think about what to deal with this. So instead, what we want to try to do is we want to try to make it look in this format where there's a single instance of one of the functions so that we can do that u-substitution very cleanly. Well, there's plenty of sines and cosines to spare in both of these. We could save a sine of x and stick it at the end, or we could save a cosine x and stick it at the end. So let's just look at two different possibilities. We could think about this as sort of sine squared, cosine to the 6, sine x dx, or we could think about it as sine cubed, cosine to the 5th, cosine x dx. Then our plan would be, in this situation, we'd be saving the sine of x dx, and in this situation, we'd be saving the cosine x dx. But let's think about one of these is far superior from the other. In this one, if we save that sine of x dx, our plan would be to do u equals cosine x. Well, that would be good for this. It would certainly be good for the cosine to the 6, but it would be sort of problematic here. But this is sine squared, which means, you guys know Pythagorean identities, we can convert this into 1 minus cosine squared so that everything is in terms of cosine except for this one thing that's going to be useful for our substitution. In this situation, things would not be so nice. Here, we'd be saving that cosine x dx in plans for doing u equals sine x, which would mean that this would be fine, but we'd have to somehow convert this. Well, even if you broke this down and you thought about it as cosine squared, and a cosine, you could certainly use Pythagorean identity there and there, but you'd be stuck with this additional cosine x. So this is not a good approach here. So in other words, we do not want to use this sort of view of the indefinite integral. We're going to instead use this one and convert this directly into cosine. So let's go ahead and do that. We can think about this as 1 minus cosine squared, cosine to the 6x sine x dx. And again, I'm sort of going to keep underlining this to remind us we're not going to mess with this at all. We're saving this to basically be a catalyst for our u substitution. Now notice if we multiply this out, everything's going to be in terms of cosine, which is great. So that's integral cosine to the 6x minus cosine to the 8th x, all times sine x dx. Now we are ready to try our u substitution. So let's do u equals cosine x. du then is going to be negative sine x dx, which is nearly perfect, right? We actually have sine x dx. So of course we'll get a negative sign. So we'll get negative du is going to be sine x dx. So that is going to match directly. So that's going to exactly match what we saved. So when we do our substitution, we're going to have the integral. That cosine to the 6 is now just going to be a u to the 6, which should be nice and easy using power rule, minus a u to the 8th, also nice and easy, times this negative du. And if we just pull that over there, we can distribute the negative sign and get u to the 8th minus u to the 6th du, just by distributing this negative onto those pieces. Now we can integrate that very easily, just with two instances of the power rule, 1/9 u to the 9th minus 1/7 u to the 7th, plus c. Then we can undo the substitution by just plugging in u equals cosine x. So we get 1/9 cosine to the 9x minus 1/7 cosine to the 7th of x plus c. And there we go. We use the same sort of trick with a little bit of sort of manipulation, specifically algebraic manipulation, using this sort of Pythagorean identity to take this sine squared and make it that 1 minus cosine squared. Notice that it is not a coincidence here that we've sort of focused on the odd exponent. That odd exponent had the property that we could pull off one of those, in this case one of those sine x's, and then what remained was an even power of sine, which we could convert using Pythagorean identity. When we get to sort of the summary of this method, that sort of noticing of the odd exponent is going to be really crucial. All right, let's go ahead and take a look at another one. All right, we're going to try to perform this indefinite integral now, the integral of sine cubed 2x. Well, first thing before we get into any sort of discussion, we are going to have to deal with that 2x a little bit. So let's go ahead and just do a standard u substitution so that we don't have that 2x inside all the time, considering that it is technically a composition. So I'm going to do u equals 2x, and du is going to be 2 dx. and then we're going to have 1/2 du is equal to dx, and we can change this into sine cubed of u 1/2 du, and let's just put the 1/2 in front, 1/2 sine cubed u du. Okay, so that's just to take care of that weird 2x in the argument. Now let's focus on this. Okay, once again, we'd like to use this sort of trick of saving one of the trigonometric functions. Well, this time there's only sine here. So let's save one of the sine of u and sort of take a look at it. So let's think about this as 1/2 sine squared u sine u du. And let's remind ourselves, I'll just underline here, that we're not going to mess with this. We're going to save this as a catalyst for another substitution. Well, if we're saving this, well, this would be the derivative for cosine. So we're hoping to substitute in u equals cosine. Of course, we won't use the letter u because we already used it, so I guess like w equals some cosine. But of course, there's no cosines over here. But this is a sine squared, so we can use Pythagorean identities again. So let's go ahead and do that. Integral 1/2, we can replace that with 1 minus cosine squared u sine u du. And if we want, I guess we could distribute that 1/2 in there just to make it cleaner looking. 1/2 minus 1/2 cosine squared u sine u du. Now, what we should be able to do is do a substitution in here. So let's go ahead and do that. We'll say w is going to be equal to cosine of u, and then our dw is going to be negative sine u du. And again, remember this part we're sort of not touching the entire time. And of course, we're going to get a negative dw is sine u du. Again, that's sort of why I reference it as a catalyst. We know that if we save that, we'll be able to do this substitution. So let's go ahead and plug that in. We get 1/2 minus 1/2 w squared, and then all that times negative dw. Notice that this is much nicer. Now everything is just going to be simple integrations. Let's go ahead and distribute the negative sign in, though, first. So we get integral 1/2 w squared minus 1/2 dw. You can drop the parentheses now. We can integrate that. Here we'll get a w cubed and then divide by 3. So we get 1/6 w cubed minus 1/2 w plus c. Now we'll need to do a little bit of unpacking. We've got to actually undo 2 substitutions here. So let's go ahead and unpack that right there. So unpacking the w being cosine u means that we actually have 1/6 cosine cubed of u minus 1/2 cosine u plus c. So there we go. That's unpacking what the w was as cosine of u. And then, remember, over here, u was equal to 2x. So we can pop that in there, and we get 1/6 cosine cubed of 2x minus 1/2 cosine 2x plus c. So there we go. This time we were able to do this, even though it wasn't technically initially a product of trigonometric functions, right? It was just the sign by itself. What we did is we said, well, this is odd, so let's save one of them. What remains will be even as an exponent. Since it's even in an exponent, we can use the Pythagorean identities to convert this into something in terms of cosine. Once it's in terms of cosine, we have exactly what we need to do a substitution for cosine, since we have the derivative of cosine right there. We went ahead and did that, and actually then undid all our substitutions for our final for our final antiderivative there. Okay, let's go ahead and take a look at a situation where we don't have an odd exponent and see how to handle that. So for the next one, before we sort of actually put a summary up for this, let's go ahead and see if we can figure out how to perform this indefinite integral, which is cosine squared. Now, this is going to be a bit harder because if you think about sort of breaking it up as cosine x dx, well, that's great, that cosine x there, right? That would be good if we could do a substitution for sine, but what would remain, since we only have 2 factors of cosine x here, is there's no way to convert this into sine, because the Pythagorean identity only works when you have a cosine squared or a sine squared. So our sort of standard trick that we've done in the last 3 examples isn't going to work so well here. So instead, what we're going to do with this is whenever we're sort of faced with a just an even exponent, when there are no odd exponents to sort of play around with, we're going to actually make use of another set of identities. So far, we've been using the Pythagorean identities. Now we're going to remind ourselves about the sort of double angle identities. Specifically, we're going to remind ourselves about this double angle identity. We saw that cosine 2x, this was a double angle identity where there are a couple different formats. There are actually 3 different ways to think about cosine 2x. We're only going to need 2 of them. You can think about that as 2 cosine squared minus 1, or you can think about it as 1 minus 2 sine squared. Well, if you think about this is an expression that has cosine squared in it that we could solve for in terms of that cosine of 2x. So let's take this version of the identity, right, this, and think about that a little bit further. Cosine 2x is 2 cosine squared x minus 1. I suppose we could go ahead and add the 1 over. So we get cosine 2x plus 1 is 2 cosine squared. And then we could divide by 2, and we would get 1/2 cosine 2x plus 1/2 is equal to cosine squared. Notice this now gives us an identity where we can replace a cosine squared with something that does not involve a square. No longer is there a square in here, it's just a normal trigonometric function. So let's plug this into here and see what we can do with that. So if we do that, we now have the integral of 1/2 cosine 2x plus 1/2 dx. So that's replacing this using the double angle identity. So there we go. Now, this is a little bit better because there's 2 terms here, and we can integrate each of these separately. So we'll have to be a little bit careful with the first piece. The reason we have to be a little bit careful is there's a 2x in there, so we're going to have to make sure that we use our u-substitution. And the second piece should be very easy, right? The integral of 1/2 dx, that's just going to be a 1/2 x. For this, though, what we should do is we should go ahead and let u equal 2x. du is going to be 2 dx, and we're going to get 1/2 du is going to be that dx there. So we're going to get another factor of 1/2. Now, as we go further and further in our class and we do more and more u-substitutions, these types of u-substitutions, which I often reference as linear substitutions because what you're substituting for is just a linear term, are things that eventually we hope we can just do in our heads, right? At this point, we should sort of start to recognize that since we're plugging in 2x and the derivative of 2x is 2, since we're doing the antiderivative, we get a factor of 1/2. And that trick works whenever the substitution is linear in nature, meaning like an mx plus b substitution. So as we start to do this, sometimes when we do this sort of substitution, we'll start to skip writing this out and just jump immediately to the result. Still the beginning of our class, though, so we're still taking the time to write it out. Nothing wrong with writing it out completely, but just be aware later on, we're getting pretty close to it actually, we'll start to actually just make this jump and just say, I know I'm going to get that extra factor of 1/2. For now, though, this should become the integral of 1/4 cosine u du. That's because we get the extra factor of 1/2, and we already had the 1/2, and there's our cosine u du. And then, of course, on this piece, we can just integrate that and finish it up, 1/2 x. We'll put our plus c once we finished all the integrals. Here, integral of 1/4 cosine u is just simply 1/4 sine u plus 1/2 x. Now we can put our plus c. And, of course, we just need to undo our substitution only into here. So we get 1/4 sine 2x plus 1/2 x plus c. So there we go. There's an antiderivative for cosine squared, which there really isn't any other way to play around with because since it's an even exponent only, there's no way to sort of save one for a u-substitution and try it our original way. So we're forced to use this double angle identity. Okay, before we get to our final examples for this, what I'd like to do is sort of summarize some of the comments that I've been making so far about the parity in terms of the even and odd exponents and exactly sort of how to generalize this approach. So we'll talk a little bit about the summary and then look at 2 last examples. So this is a summary for integrals of products of sine and cosines. In the next video, we'll talk about a summary for integrals of products of tangents and secants. But for right now, we're on products of sines and cosines. So if you have an indefinite integral of the form integral sine to the n cosine m dx, then this is how you should attempt to integrate it. If at least one of the exponents is odd, so if either n or m or both of them are odd, then what you want to do is you want to save one factor from whichever one has the odd exponent, and then convert the remaining ones using the standard Pythagorean identity. This will always be possible because if you have an odd exponent and you save one factor, then what remains will be an even exponent, and you can, of course, by just using successive iterations of the Pythagorean identity, convert that into the other trigonometric function. Since one of them is odd and you save one of those factors, then you can always finish it up by using u-substitution. So in other words, if at least one of those exponents is odd, that's the nice, easy case where you save one, do some conversions, and then u-substitution. Unfortunately, if both exponents are even, then you will need to use this double angle trick, and you will need to use one of these two expressions. Sine squared can be converted into 1/2 minus 1/2 cosine 2x. Where am I getting that from? Well, that's from using this one here, so setting it equal to this and then solving for sine squared. I'm not going to go through that derivation, but if you do, you will get this expression here. Or cosine squared can be converted into 1/2 plus 1/2 cosine 2x. So probably a good idea to note down these two identities, because in this sort of integrating of products of sines and cosines, you will often see this sort of use. So these are two good identities to definitely have memorized. Okay, so now that we have this summary, let's take a look at two more examples, and we should be able to go through, even though these examples are a bit harder, we should be able to go through them almost as quickly because we have this nice summary now. Okay, so let's try to go ahead and perform this indefinite integral. Sine to the 6x cosine to the 5th x dx. Do we have an odd exponent? Yep, we do, right? We can see that there's our cosine to the 5th, right? So there's our odd exponent. So we know that we should save one from here and then convert the rest. So we should rewrite this as sine to the 6x, cosine to the 4th x, cosine x dx. So we save one from the odd, and at this point, if it helps, write something to remind yourself you don't want to mess with this at all. This right here is perfect for the du if we do u equals sine x. So this is good, this is good. We need to convert the remaining cosines. To do that, since it's cosine to the 4th, we can think about it as sine to the 6th, cosine squared, cosine squared, cosine x dx. And again, never going to mess with this. Each of these cosine squareds we can use our Pythagorean identity on. So integral sine to the 6th, 1 minus sine squared, 1 minus sine squared, cosine x dx. We could go ahead and u-sub right now, but I'm going to go ahead and multiply this stuff out just so we can sort of take a look at it. This is now the integral sine 6x. If I FOIL these guys together, it looks like I'd get 1 minus 2 sine squared plus sine to the 4th x. And of course, the cosine x dx just keeps tagging along. And then if you want, you can distribute this onto each of the three terms. So we now have the integral sine to the 6th minus 2 sine to the 8th plus sine to the 10th. And all of that is multiplied with the cosine x dx. Notice I definitely don't want to distribute the cosine x dx in there or anything, because we know we're saving that as a catalyst for our u substitution. Now we let u equal sine x. du is going to be cosine x dx. That's exactly what we have there. So this substitution is going to be nice and easy. This should now become the integral u to the 6th minus 2u to the 8th plus u to the 10th, and then all that du. So we can then go ahead and just use power rule 3 times. Looks like we should get 1/7 u to the 7th minus 2/9 u to the 9th plus 1/11 u to the 11th plus our constant of integration. Then just simply plug back in that sine of x. So 1/7 sine to the 7th x minus 2/9 sine to the 9th x plus 1/11 sine to the 11th x plus c. So there we go. There's our antiderivative for sine to the 6th cosine to the 5th. Had an odd exponent. We grabbed one from there and then pretty much proceeded through some algebraic manipulation and a u-substitution. All right, let's go ahead and take a look at one last one. We're going to try to perform the indefinite integral, the integral of sine to the 4th x. We're not thrilled when we see this because this right here is going to be even. So we're not going to be able to use our u-sub approach. Instead, we're going to have to use that approach we mentioned on the previous page using the double angle. So that double angle is going to let us convert these sine squared. So we'll take our sine squared. Then we said that sine squared x can be thought about as 1/2 minus 1/2 cosine 2x. Right? We can double the angle and get that 1/2 cosine 2x. So we're going to replace that in each of these. So we have the integral then, 1/2 minus 1/2 cosine 2x times 1/2 minus 1/2 cosine 2x dx. Let's see what happens when we FOIL that all out. So if we FOIL that out, we get 1/4. And then looks like we get a minus 1, so minus 1/4, double it, minus 1/2 cosine 2x. And then we get a plus 1/4 cosine squared 2x dx. Okay, we're happy about this. We're sort of happy about this. I mean, it's not the best because we got that cosine 2x in there. But again, this should be pretty easy. We can u-sub it, or we can use that linear substitution idea I was talking about to handle this. And then we've got this guy. We're definitely not thrilled about this because this is still even. But it's better than it was before because originally we had a to the 4th power. Now we have it down to the 2nd power. So let's split this into a couple different integrals. So we have the integral of 1/4 dx minus the integral of 1/2 cosine 2x dx, and then plus the integral of 1/4 cosine squared 2x dx. So let's handle all the pieces we know how to handle before looking at this one. So this should become 1/4 x. The integral of cosine we know is going to be sine, but since we have that 2x, we get an extra factor of 1/2. That's that linear substitution. Going to not write out that u-sub now. So minus 1/4 sine 2x. If you want, you can check by differentiating this using chain rule. Derivative of sine is cosine. Derivative of that 2x is going to be 2. The 2 comes out, mixes with the 1/4. That's what gives us our 1/2. So there we go. And what about this? Well, it's a cosine squared, so we can use this double angle here. It's 1/2 plus 1/2 cosine 2x. Now, the only difference, though, is that ours is cosine squared 2x. So that should be 1/2 plus 1/2 cosine 4x, because this doubles the angle. So if we have 2x in there, we're now going to have 4x. So this should convert then to plus the integral of 1/4, parentheses 1/2 plus 1/2 cosine 4x dx. Okay, so we're saying that this cosine squared is replaced with 1/2 plus 1/2 cosine of the double angle. Since we had 2x as the argument, now we have 4x. Let's go ahead and simplify a little bit. We've got 1/4 x minus 1/4 sine 2x plus the integral 1/8 plus 1/8 cosine 4x dx. Okay, we still have an integral to do, but everything is nice and easy now. This is a constant. This is a trigonometric function, yeah, with a linear substitution, but we're comfortable with that. 1/4 x minus 1/4 sine 2x plus 1/8 x plus, we'll get an extra factor of 1/4, and the integral of cosine is sine, so we get 1/32 sine 4x plus c. Any last things to do? Sure, we can put the 1/4 and the 1/8 x together, and I guess the best expression would be 3/8 x minus 1/4 sine 2x plus 1/32 sine of 4x plus c. And there we go. This shows you guys an example of where you had to use the even sort of approach, meaning the double angle identity approach, twice, because we started with a sine of 4 sine to the 4th x, split it into a pair of sine squareds, used the double angle, multiplied that out. It turned out that most of it was doable, but one term still had an even exponent. So we did the double angle identity just on this part again, and then finally we were all good. We had no more exponents, no more products, so we were able to integrate directly. Had to be a little bit careful because of the 4x, which caused us to get an extra factor of 1/4. Otherwise, though, we were able to get our antiderivative there. In the next video, we'll finish up section 7.2 by looking at a similar analysis to what we just did here, but for products of secants and tangents.